Hey folks, welcome to this episode on energy changes and particularly enthalpy. So, we were looking at different definitions before: temperature, thermal energy, and heat. Now, enthalpy is another definition, but in this case, what enthalpy is a measure of the total kinetic and potential energy in a system. Now, if you're thinking that might sound a little bit familiar, remember that thermal energy was the total amount of energy, of kinetic energy in a system, but enthalpy measures both the potential and kinetic. Now, if you're thinking this might be hard, it actually is. And so we have a little bit of a roundabout from that. Now, enthalpy is what we call a state function. So when we look at this diagram over here on the right, what we can see is that this person, we're assuming there's a person here, is climbing up this mountain. Here's your starting point, here's your final point. There are different routes to get from the starting to the final point. You could either go a direct route up this way, or you could take more of the scenic route and go this way up there. This is what we call a state function, where it doesn't really depend on how you get there. It only depends on where you start and where you finish. So what this means in terms of chemistry is that we can figure out this change, in this case in height, but we're going to relate this back to what we call enthalpy. We can determine this enthalpy change by either doing one reaction or maybe doing a number of reactions to do that. The sum of those individual reactions will give us the overall one reaction. But don't worry, we'll get there. So, it is very, very difficult to measure all these kinetic and potential energies. Remember that kinetic energy could be rotation, translation, but the potential energy is particularly hard because potential energy is stored in the bonds and also in the nuclear forces that actually hold the protons and the neutrons together in the nucleus. So we'd actually have to destroy all of that, and then you can go even further where we have quarks that are producing the protons and the neutrons. So it's very, very difficult to figure out these potential energies. So instead, we do a little bit of a roundabout. We acknowledge that we can't really do it, so we look at just the enthalpy change. And so what this is the difference in the enthalpies when we compare the reactants and the products during some kind of change. Now remember, there's chemical, there's physical, and there's a nuclear change that we can look at. So looking at this diagram here, where we have methane reacting with chlorine, these are our reactants. Okay, so our reactants, they're the things that are reacting, and here are our products. Now, in the course of this reaction, these reactants, the bonds between the reactants, so these are all covalent bonds here, they'll be broken. And the way that they're broken is by actually absorbing some energy. You need to break, think about it as twigs. You actually have to put some energy into breaking those twigs. So we have to break these twigs between these atoms to have them separated. Now sometimes we don't have to separate all of them, maybe just one goes at a time. But the key part here is that we have to absorb energy into the system to break these individual bonds. Then we separate our atoms over here. At this point, this reaction can go one of two ways. It can revert back to the original reactants, or it can go on and produce some kind of new products. So when it produces products, it forms new bonds. So in this case, you can see that the chlorine here bonds onto the carbon here, and this hydrogen bonds onto the chlorine here to produce two new products, hence the chemical reaction. Now you can see that going from this reactants, yes, we've added some energy to break the bonds, but we've also made that energy up when we've formed new bonds. Not only that, but we've actually released even a little bit more energy. As you could probably guess, this is our enthalpy change, and this enthalpy change comes out as heat. Now heat we can measure using temperature. Okay, so we can't really, there's not really one way of determining what the enthalpy change is, but we know that this enthalpy change is going to be released as heat, and we can measure that heat using temperature. So if we know what the temperature change is, we can calculate the heat, and then we can calculate the enthalpy. I'm going to say that again because that's actually a really, really important point that we're going to be using for a lot of our calculations. Once we know what the temperature change is, the initial temperature and the final temperature, we can backtrack and calculate heat, and from that we can calculate the enthalpy change of the system. So how does this all work? Well, this goes back into what we were talking about between the system and the surroundings. So remember, the system is where the reaction is actually occurring. So we can think about this as our system, and everything else is the surroundings. One important point to think about it, going back to the previous slide, is heat. Enthalpy is again the total amount of kinetic and potential energies within a system. That's caused by kinetic energy like movement of the molecules and also bonds and other forces that keep the atoms and the molecules together. So if we know that this enthalpy increases, the only way that you can add energy to a system, going back to our law of conservation of energy, means that it has to have gained it from somewhere. And where it gains it from is from the surroundings. So heat is going to be going into our system. Now think about it. If heat is going into our system to increase its enthalpy, its potential and kinetic energy, that means that heat must be lost in the surroundings. Now if heat is lost in the surroundings, that means that the thermal energy of the surroundings decreases, and temperature and thermal energy is directly related. What we'll see is a decrease in temperature. Okay? So if we see a decrease in temperature, something that we can measure, we can assume that some of that, assuming that we have an isolated system, that we haven't lost heat to the surroundings, but that the system is taking in that heat or that thermal energy and its own enthalpy is increasing. Now, the same happens over here. If we feel that if we see that the temperature is increasing, that is as a result of thermal energy being transferred from our system into our surroundings via heat. And that heat is causing an increase in temperature change. So from this temperature change that's increasing, we can assume or we can propose that the enthalpy of our system is decreasing. The only way that the surroundings could gain heat is for something to be losing that heat. And that is, again, going back to our law of conservation of energy. So just a little point here, going back to our chemical reactions, physical and nuclear are happening a little bit different, but when we talk about our chemical reactions, these chemical reactions occur in a number of steps, and thermochemistry is all about the study of energy. So what we're going to do is take a pause here and look at what is actually happening. Again, here we have our reactants, and like we said before, for these bonds, these little sticks between these atoms to actually break and create these collection of separated atoms that eventually will form our products, these bonds have to first be broken. So to break those bonds, just like snapping a tree twig, we require some kind of energy. So breaking bonds requires some energy. That process of taking in energy is what we call endothermic. Now, where does it get its energy from? You guessed it. It gets it from the surroundings. So this first part over here is an endothermic reaction, meaning the system is absorbing energy from the surroundings. Now, if we're looking at our Q functions, what that means is that the system, the Q of our system, is going to be positive. The Q of our surroundings is going to be negative. Now, if we also think about it, what kind of temperature change would we see here? We should see, because that's what we're measuring the temperature of our surroundings, we should see a decrease in temperature. So as these bonds are broken and they form these separated atoms, they will form new bonds. Now, when we look at this process is what we call exothermic. So the formation of new bonds releases energy. And where does it release it to? Well, same place it got it from, into the surroundings. So in this case, what we can assume is that because energy is being lost from the actual system, the surroundings is gaining that energy. So the Q of the surroundings is going to be positive, and the Q of the system is going to be negative. Now, one step further, remember that Q is related to enthalpy. The only way a system can lose heat is by actually changing its own internal kinetic and potential energies. So what we're saying here is that our enthalpy for the system is negative. The system is changing its enthalpy. It's converting some of that potential and kinetic energy and releasing it as heat into the surroundings. Going back to this example here, because the system is gaining energy from the surroundings, the system is increasing its enthalpy, so the delta H is going to be positive. Now overall, what we can see, yes, there's an endothermic and an exothermic part to this, but what we can see is that there has been energy put in and energy released. But there has been more energy released than there has been put in. This is our delta H, okay, and this is our change in enthalpy. Now overall, just kind of stepping a few steps forward, because we've released more energy than we've put in, overall, if we put our hands over this reaction, we will feel heat. So heat is being ultimately released. And so this overall reaction is going to be considered an exothermic reaction because it has lost more heat than it originally put in. So again, lost more heat than originally put in. So an exothermic reaction, again, our chemical system is losing its thermal energy, it's transferring its thermal energy from the system to the surroundings by loss of heat. The only way that it could lose heat from the system that way is by itself reducing its potential and kinetic energies. So that means that its delta H, or its enthalpy, its enthalpy is decreasing. Okay? What that means is that the Q of the system is decreasing. The heat of the system is being lost. Remember that the negatives show it's either been gained or lost. Now, if we are looking at the surroundings, for example, because the system is losing heat, the surroundings must be gaining it, and so its value is going to be positive. So because the surrounding is gaining some heat, we will see an increase in temperature, and that's what we can use to help us figure out whether or not this chemical system is gaining or losing heat, or aka increasing its enthalpy or decreasing its enthalpy. So again, the way that this happens is that we have reactants. This is an endothermic process. Bonds have to be broken, so energy is absorbed. And then when these atoms reform, they release energy, but because more energy was released than gained, overall there's been a release of energy into the surroundings, and it's going to be called exothermic. On the flip side, something that is endothermic means that the chemical system, whatever the particles reacting are gaining energy from the surroundings. So the surrounding, in this case, the Q, would be negative, and for here, the Q would be positive. Now, because the system is gaining heat, it converts it into enthalpy, and so our enthalpy would be positive. Okay? Now, because we are measuring the temperature of the surroundings, again, this is a key part. We're not measuring the temperature of the system, we're measuring the temperature of the surroundings. So because we are measuring the temperature of the surroundings, and the surrounding is losing its heat, aka it's losing its thermal energy, we will see a fall in temperature. Now, how does this happen? Well, here we have reactants, and here we have our products. And what you know is that more energy has been taken into the system to break the bonds than released when new bonds are formed. So overall, we've added more energy than we have released in creating those new products, and so this is called endothermic. Now, sometimes we express these enthalpies as something called a molar enthalpy. Now, this is very, very an important point here, because when, for example, you go car shopping, you look at car A and car B, you're probably looking at similar cars. Now, if you're looking at a Honda, you might be looking at something like a Toyota or whatnot. But you probably wouldn't compare a Honda with maybe a McLaren or a Lamborghini. Okay? They have different features that are not directly relatable. And so in the same thing, what we try to do is we try to look at the molar enthalpies that are released based on a per mole basis. Some of these, based on the balanced equation, might have many, many moles of products or many, many moles of reactants done and reacting or produced. And so this number can get very, very complex. What we want to try to do is we want to try to standardize it and use it on a per mole basis. Now what you see here is delta H. What you see there is there's a little x there. And that x is just a variable. That x will change depending on what the definition is. So some of the things that you might see is delta HF for formation, the formation of a product, or delta HC, which is the combustion of a product, or delta HNEUT, or just N, which is the enthalpy change of a neutralization reaction. So this subscript can change depending on what you're measuring. Now that's a key point, is that if these subscripts change, the definition also changes. Now we're going to get into this a little bit later, but let's take, for example, this example over here. In previous slide, you might have seen this example, just kind of worked out. I didn't really talk about it too much. But for 2 moles of hydrogen to react with 1 mole of oxygen, remember that hydrogen is a single covalent bond, oxygen is a double bond, and then here we have H2O, and we have 2 of these, and we have 2 of these. So for this reaction to happen, we have to break 2 moles of these. So basically we're breaking 2 hydrogen-hydrogen bonds. We have to break 1 oxygen double bond, And what we see is that we have to break, or we have to form an oxygen-hydrogen bond, an oxygen-hydrogen bond, and we have to form another two of those for the other molecules. So all in all, we're forming 4 OH bonds. Now, there's a certain amount of energy that is required to break these bonds, okay, and the amount of energy to break a hydrogen bond like that, or not a hydrogen, but a covalent bond between hydrogen, is 436 kilojoules. Now, because I have 2 of them, I'm going to multiply that value by 2. And what I get for that, and it's a little bit sloppy here, not too much room, I get 872, and that's positive because I need to put that into the system. This is an endothermic reaction. Now, for our oxygen, the amount of energy required to break one double bond of oxygen is positive 495 kilojoule. So altogether, I have to put in positive 1367 kilojoules to break the bonds between hydrogen and oxygen. Now, when I form this water, I'm forming, now each OH bond will release, the formation of each OH bond will release 463 kilojoules. But like we said before, in one molecule of H2O, there's 2 OH bonds. There's 2 of them, so I need to multiply this by 4. And what I get is I get negative 1852 kilojoules. So when I look at this, to break the bonds between these reactants, I need 1367 kilojoules of energy to be input into the system. So that means that the surroundings need to lose this, and the system, aka it has to gain this, aka meaning that its enthalpy increases by this much, the enthalpy, the kinetic and potential energies in these molecules. Now, when they're all broken apart and they form water, each of these OH bonds will release 463 kilojoules, but because I have 2 of them in each molecule, and I have 2 molecules, I multiply by 4, and in total, I'll release just because that's the negative, so that negative tells us that it's released, I'll release 1852 kilojoules. So overall, what I want to try to figure out is this reaction endo or exothermic? And I look at how much energy I had was lost by the creation of bonds versus how much energy I put in, and the difference, what I get, is going to be negative 485 kilojoules. And that's what I get right over here. Okay? Now, it's on the product side, so this is reactants, these are your products. It's on the product side because it shows that this energy is being created. It's being produced. It's being released. And so because it's being produced or released, it's on the product side. If this was an endothermic reaction in general, you would find that term over here, but we'll get to that a little bit later as well. Now, we've also expressed this value over here as a delta H, the change in enthalpy, how much was put in versus how much was released, is negative 485. Why the difference in operator? This is part of the equation. This is a standalone term. That negative shows us that it's been released. The position of this value in this overall term shows us that it's been produced as well. So what we can see is when 2 moles of hydrogen, 1 mole of oxygen produce 2 moles of water, we have 485 kilojoules released. Now again, when I look at this reaction, let's say for example I want to use this for fuel for a hydrogen car, I want to figure out, well, if I burn 2 moles of hydrogen, how much energy would I get if I burn 2 moles of gasoline? Would I get the same amount of energy? Because I want to get the most amount of energy out of this. So will it be the same? The only way that I can figure that out is by standardizing. And so in this case, because water is being formed, I can use something called the delta HF, or the delta H of formation, the enthalpy change of the formation. And this particular value, the definition, is the enthalpy change when 1 mole of product is being produced. So what I have to do is I have to make sure that my coefficients are actually broken down so that I get 1 mole here. Now sometimes you might get fractions, and that's okay. Here I'll get 1 more, here I'll get a half, here I'll get 1 mole by dividing everything by 2. And I also divide my enthalpy by 2. So I've taken my kilojoules, how many kilojoules were released in this reaction over here. I divide it by 2 moles, and what I get, so I take my negative 485 divided by 2 moles, over here, 2 moles over here, and I get 242.5 kilojoules. So again, I can express that as delta HF as negative 242.5 kilojoules per mole. Now, we are going to talk about this a little bit further, but again, this is a very, very important thing that we're going to talk about because most of our calculations are going to be in this molar enthalpy and also something called a standard molar enthalpy. Thanks very much for watching. Hope this helped. See you next time.